So here we can see a cantilever beam that's supported on the left side, has an even distributed force acting on it, and two concentrated moments. One with 100 kilonewton per meter, 100 kilonewton meter, and another one with 100 kilonewton meters. And now we are asked to find all support reaction for that cantilever beam. As always, let's get started with our free body diagram. So I am copying this system down and I will use all my forces. For example, here the 100 kilonewton meter, and then here my 150 kilonewton meter, and of course also my evenly distributed force, which is acting over 4 meters. So let's now go ahead and add the support reaction RAY, RAX, and MA about the z-axis. All right, and that's all we need to get started. So let's go ahead and run our calculations. So to find RAX, all I have to do is take the sum of the forces in the x direction being equal to 0, and therefore 0 is equal to RAX. And that is a result once again. To find RAY, what I have to do is take the sum of the forces in the y direction and set it equal to 0, upwards positive, and 0 is equal to plus RAY minus, and shame on me, I didn't calculate how much this is, so this is 20 kilonewton per meter. So 20 kilonewton per meter is now going downwards, so minus 20 kilonewton per meter multiplied by 4 meters. It's acting over a distance of 4 meters, and therefore I know that my RAY, first of all, is positive, and I indicate that it's positive, and then 20 times 4 is 80, plus 80 kilonewton. This means it's going up. All right. Now, last but not least, we have to move on to the moment equation. But before we move on to the moment equation, note that in this equation, these two concentrated moments had no impact. They were not included in my equation, and they are not part of anything here because, as I mentioned to you before, there are no forces that are not in balance, and therefore they don't have to be added here. It would be incorrect to add them. Now for the moment about A, we would take the sum of the moment about A and set that equal to 0, counterclockwise positive. And I assumed that to be clockwise, so therefore 0 is equal to minus MAZ. And let's start with the 20 kilonewton. That would rotate, of kilonewton meter that is, that would rotate clockwise, so 20 kilonewton per meter multiplied by 4 meter. Notice that it's not a moment yet, it's only a force because those two cancel out. So I have to multiply that by the lever arm, which happens to be 4/2 meters. And again, that rotates clockwise, therefore this is negative as well. And now I have to add my two moments. So I have the 100 kilonewton meter, and that one rotates counterclockwise, therefore it's positive, and the other one rotates clockwise, so therefore it's negative, so minus 150 kilonewton meter. And yes, it is that simple. But don't worry if you get confused why we're even learning this if it's so simple. You will see later on when we deal with internal forces that they will have to be dealt with in a very special way. This is just to get you used to these concentrated moments and what effect they have on the two different types of equation, force equilibrium and moment equilibrium. So you'll see that here we just added them depending on their rotational sense. Last thing for us to do is to find the answer to MAZ, which in this case comes out to be negative 210 kilonewton meter. So in other words, my MA about Z is actually 210 kilonewton meter, and that rotates counterclockwise, right? So counterclockwise or this way around. And that is my true answer here. So this needs to be double underlined and also needs an answer arrow, as do all the other ones for this example. So let's finish that. And this is now done, and we completed our first cantilever problem with concentrated moments, and we know now how they affect our equilibrium equations for forces and our equilibrium equations for moments, or I should better say how they do not affect our force equilibrium equations but our moment equilibrium equations. So that completes our lecture, and we can now move on to the homework and to the conclusion of our learning experience.